So quantum computers right now, we have quantum computers that do work here at IBM. But the challenge with quantum computing is we need to make them bigger, better, faster, stronger. So you can think of it similar to an analogy of normal computers. Decades ago, they were very large, they took up entire rooms, and they could barely do anything, right? We're kind of at that stage right now with quantum computing. And the challenge with quantum computing, the reason why we need, young minds to get into quantum computing is we need some very clever ideas to help us scale quantum computing to larger sizes so that we can solve much more practical problems. So yes, every day in our labs, we work on these forms of quantum computers every day to do research and to learn how to make them better. That's really the main focus of what we do here at IBM, is trying to improve the quantum computing so we can make it useful for the world. Good question. Quantum question over there. Oh, that's an excellent, excellent question. Okay. So quantum... yes, I'll repeat it. So why does a quantum computer need to be 100 times colder than outer space to work? That's a wonderful question. So if we remember that quantum objects, right, they have to be very, very tiny in order to live in the quantum world, right? But I can see some of the things that are in this quantum computer. So if I can see them, how do they live in the quantum world? So by cooling everything down to very, very, very cold, we actually can make bigger things that we can see act like they follow the rules of quantum physics, right? It's very hard to work with really tiny things in individual atoms, and people actually do that. But the way that we do it at IBM is we use something called a superconducting circuit, and we get that really cold. And when that superconducting circuit gets really cold, it starts following the rules of quantum physics. Good question. Yes, right there. How big is the quantum computer? Okay, so you can kind of see, this is my friend Micah right here. The quantum computer is probably, if you had to imagine it here, it takes up this entire, from here to the wall, all the way to the TV, and then it goes probably like 10 feet in the air, and it actually hangs from the ceiling like this. Let's see if I can. So it hangs from the ceiling like this, so it's very big. And so when you actually need to open the quantum computer up, you need two people because these cans that go on the outside are very, very heavy. Right there, in pink.
How long does it take to build?
How long does it take to build one? Well, that's a great question. So let's say you have all the parts ready and you know exactly what you need to do to build one. It takes actually only a few weeks to put everything together. But the real challenge is developing the technology that goes into it. So some of these little individual scientific elements that you see in this quantum computer, those took years and years and years to figure out how we can actually make them work at a quantum scale. So physically building one is not as challenging as you might think. And that's actually something really important, because if we want to have a lot of quantum computers in the world, they have to be easy to build. But we can only make them easy to build if we do the really tough science to figure out how to make it easy to build. Good question. Right there.
What's the greatest achievement that the quantum computer has done?
Oh, that's a really, really good question. What's the greatest achievement that a quantum computer has done? So there are some problems that other scientists and chemists, for example, they need to understand the way that molecules interact with each other, right? So like Dr. Lauren in our story. So there have been some achievements done by scientists where they have interacted molecules together, and that has caused them to gain a much, much better understanding of their molecules and the world around them. So you might say, okay, that's like kind of esoteric, that's kind of crazy, right? And that's the thing with quantum computers right now, is they're mainly a tool for scientists to discover very, very, very hard things and to figure out very, very hard things that'll help them eventually create something big for the world. So the example, like Dr. Lauren, like if she was able to find a cure for a very deadly disease, that would be a very good thing for the world. Good question. Okay, any other questions? All the way in the back over there.
How long does it take for it to figure out the quantum?
Okay, excellent question. That's a really good question. So remember we said like the normal computer would take like 100 billion years, right? And so because the quantum computers are able to run different types of problems and run different programs and algorithms, they can take those problems that would, take hundreds of billions of years and solve them in a matter of hours or days. But it very much so depends on the type of problem that you're trying to run. If you're running a very big problem, it might take days or hours. If you're running a small problem, it might happen immediately, basically. So that's another part of quantum computing, is understanding how we can actually make things run faster. Great question. Right there.
There's stuff inside it.
Okay, really good question, a really hard question. So remember, the quantum tennis ball, we're just using our imaginations, right? So of course this isn't a real quantum tennis ball because it's too big. But if it was a quantum tennis ball, what can happen is, I'm going to start getting into the physics here. The quantum tennis ball, when it lives in the quantum world, it is actually both what's called a particle, so something that you can touch and you can see, right, and a wave. So when it's traveling through space, it's moving, and it has its wave-like properties. And that wave-like properties essentially creates a cloud or a distribution of where it's physically possible for that individual particle and wave to exist. So what happens is the particle has energy as it's moving towards the wall. It has energy. And once it hits the wall, if it actually has enough energy, there's enough of a chance, right, in what's called that quantum wave function, that the particle, even though it has mass, even though there's stuff inside it, even though there's stuff inside the wall, that there's a chance, if it has enough energy, that it will actually go through the wall. That was a very tough question. That's a really hard one to understand about quantum physics. In the blue back there. Yeah, good question. So that one is because when two quantum objects, okay, so let me repeat the question actually. He said, how do I know when I flip two pennies, if I only measure one, how do I know for sure the other one? And so when two quantum objects, they interact with each other, right, they create a promise with one another. And that promise that they make with one another, that quantum link, is a very special property of quantum physics. That's just the way that the universe works in this sense. So because those two pennies make that quantum promise with one another, they know effectively, well, I don't want to say something incorrect here, so this is where it's getting hard with the science. The quantum pennies, they create a promise with one another, and they're linked, right? And so no matter what, if I observe this quantum penny as heads, I will know that this other quantum penny is heads, just because of the way that quantum physics dictates the world. Another tough question. Let's do all the way back there.
How does the quantum computer function?
I love that question. Okay, so a quantum computer, to build one, it costs millions and millions of dollars to build one. And that's not including all the money that we spend, paying researchers and scientists to do research. That's not including all the money that it takes to, spend decades learning and doing science and failing and succeeding and failing and succeeding. But to actually build one with all the parts that we have now, millions of dollars. Right there. Yes, I will. I'll come back to you. Next question, right there. Say again? If it crashes? Well, I would say this. Quantum computers, right, they probably crash a lot more than normal computers do, right? Because they're so experimental, because they're so much in the research phase, there's actually a lot of problems that we face every single day that's effectively like our quantum computer crashing. But the good thing is nothing catastrophic happens. Nothing blows up or anything like that. What's that? Actually, it depends on the type of failure, right? If something happens with the hardware, that can cost a lot of money. But if you're just trying to run a program and it crashes, you just reset everything and it's all good. Okay, questions. I come back to you.
Last 3 questions.
Last 3 questions. Okay, so coming back to you.
Does the penny, like a regular penny, is that like a quantum pen, or do you have to have like a special pen?
Okay, so the question was, it's a good question too. The question was, can a regular penny act like a quantum penny, or do you have to have a special penny? So in order to have something live in the quantum world, it generally has to be very, very small. So this penny is ginormous, right? Of course, this is not a real quantum penny because it's huge. So we just, for the example, using our imaginations. But if we were to make this a quantum penny, we'd have to make it very, 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 very small, like the size of an atom or a few atoms. Okay, so 2 more questions, right? Back there. You're affected. I think what you're asking is like, can I take the information or whatever's stored in the quantum penny and can I transfer it over to something else? Kind of? Is that kind of what you're asking? Yeah? So that's a really good question because there's something in quantum called the no cloning theorem. It's basically just a very fancy way of saying that you cannot replicate the information that's stored in a quantum particle. Really good question. Okay, so last question. Last question. Who hasn't asked a question yet? You haven't asked a question yet. What's your question? How do I use a quantum computer? Oh, that's a great question. I love all these questions, you guys. You guys are making me very happy. So, okay, on a daily basis, here's kind of how it works. So we build the quantum computer, and then when we want to study it, when we want to measure it, what's actually really great about the technology that IBM has developed is it's as simple as taking out your laptop and running a few commands, and then your laptop will send a signal to some special electronics in the room, same room that the quantum computer lives in. And then from those special electronics that the quantum computer lives in, those electronics will send a signal all the way up into the quantum computer, all the way down to minus 460 degrees Fahrenheit. And then the quantum computer, those qubits down in the bottom, will send a signal all the way back up. They'll go back through those same electronics, and then it'll send another signal to your computer. So when I actually want to run something on a quantum computer, it's awesome. All I have to do is just run some commands, and I see the output. It's wonderful. All right. I think that's all the questions we have time for today. Thank you again, everyone. It makes me very happy to see everyone here today. Do good work and have fun today.